All right, let's get right into it. If you think about it, your network switch is kind of like the central nervous system for all your devices. Everything connects through it. And if that switch isn't locked down tight, well, your whole network is basically an open book. So today, we're going to build a fortress. We're going to walk through the absolute must-know techniques to secure this critical piece of your network.
So, here's our game plan. We're going to start with the front door, the most basic physical connection, that's port security. And from there, we'll just keep building up our defenses layer by layer. We'll tackle VLANs, then DHCP, ARP, and finally, we'll secure the very foundation of the network, the spanning tree protocol itself.
Okay, first things first, our first line of defense is all about controlling who can even plug into the network. I mean, at the most basic physical level. This is about securing the front gate before an attacker even gets a chance to step on the property.
Now, it's kind of interesting what an attacker is trying to do here. They're not trying to steal your data, not yet anyway. Their first goal is just to break the switch's brain, that memory table it uses to keep track of everything, by just spamming it with thousands upon thousands of fake hardware addresses.
And when that happens, well, the impact is huge. Once that memory table is full, the switch basically has a meltdown. It completely forgets who is connected where, and in a total panic, it just starts shouting all the traffic out of every single port. And just like that, all your private network traffic is being broadcast for anyone to see. It's a massive security failure. So how do we stop this? The answer is actually pretty simple, but incredibly powerful. Port security. Think of it like putting a bouncer on every single port. You set the rules. Hey, only one device is allowed in through this door, and it better be on the guest list. If anything else shows up, it gets dealt with. And here's a super important real-world tip you've got to remember. A switch needs to know what a port's job is before you can secure it. You have to tell it, hey, this is an access port. It's for a regular computer. And only then will it let you add the security commands. It's such a common gotcha, so don't forget it. Okay, so that guest list. How do we actually build it? Well, you could type in every MAC address by hand. That's super secure, but man, what a pain. Or you could let the switch learn it dynamically, but then it forgets everything if it reboots. And then there's the best of both worlds option, sticky. The switch automatically learns the MAC address of the first device that connects, and then it writes it right into the configuration for you. It's super effective and so much more efficient. So what happens when our bouncer actually catches a party crasher? You've got three choices. Shut down is the nuclear option. It just turns the port off completely. Done. Restrict is a little more nuanced. It drops the bad traffic, but it keeps the port open for the good guy, and it sends you an alert. And then there's Protect, which just silently drops the traffic. You get no alert, no visibility, which honestly makes it the least useful of the three. So the front gate is secure. Awesome. Now it's time to reinforce the internal walls of our fortress. This next layer is all about stopping an attacker who might already be on the network from, breaking out of their little corner and hopping over into a more sensitive area where the important data lives. And attackers have some pretty clever ways of trying this. They can try to trick a port into thinking it should be a trunk link, which would give them a free pass to all the VLANs. They might just plug in their own rogue switch. Or they can get really fancy and use a sophisticated double-tagging attack to try and sneak a packet into a secure VLAN. Fortunately, the fix for this is actually really straightforward. You just have to be explicit. Don't let your switches try to figure things out for themselves. You tell every single port what its job is. Access ports, you manually set them to access. Trunk ports, you manually set them to trunk. And then you turn off that automatic negotiation protocol, DTP, everywhere. As a final step, change the native VLAN away from the default of 1. It just makes things that much harder for an attacker. Okay, let's move on to our third layer. Every single device on your network needs an IP address to get online, and that's all handled by DHCP. But this critical service can be abused by attackers to either knock everyone offline, or worse, put themselves in a position to intercept everyone's traffic. So, the two main attacks here are starvation and spoofing. Starvation is basically a denial of service attack. The attacker just keeps requesting IP addresses with fake MACs until there are none left for the real users. But spoofing is way more sinister. Here, the attacker sets up their own fake DHCP server so they can trick users into sending all of their internet traffic through the attacker's machine first.
So, how do we stop this? We use something called DHCP snooping. Just think of it like a special firewall built specifically for DHCP traffic. It works on a really simple principle.
you tell the switch which ports are trusted. Those are the ones that lead to your real, legitimate DHCP servers. And it automatically treats every other port as untrusted, where it inspects every DHCP message very, very carefully.
But here's the real magic of DHCP snooping. It's the database it builds. By watching all those legitimate DHCP transactions, it creates this incredibly valuable map, what we call our source of truth, that reliably links a device's hardware address to its IP address and even its physical location on the network. This table is going to be critical for our next step.
And that source of truth we just created, it's the key to our next layer of defense. We're going to use it to protect another one of those fundamental protocols called ARP. Now, ARP is how devices find each other on a local network, but it was designed a long time ago with basically zero security in mind, which makes it super easy to abuse. The classic attack here is called ARP poisoning. An attacker just starts shouting out fake ARP messages, basically lying to everyone on the network. They'll say something like, "Hey, everybody, if you're trying to reach the internet gateway, send your traffic to me instead." And if other devices fall for this lie, the attacker becomes the man in the middle, seeing and intercepting everything.
And this is where that layered defense strategy really starts to pay off. The solution is called Dynamic ARP Inspection, or DAI, and it works because it can check that binding table we just built with DHCP snooping. It validates every single ARP message against our trusted source of truth before it allows it to pass. No match, packet gets dropped. Simple as that.
Now, if you want to get even more secure, DAI can do some extra sanity checks. It can check to make sure the MAC address in the Ethernet header actually matches the one inside the ARP message itself. It can also check for bogus IP addresses. These extra checks just help weed out any weird, malformed packets. A quick pro tip, though. You usually have to configure all of these checks on a single command line for them to work together.
Okay, we're at our final layer. We've secured the ports, we've reinforced the internal walls, and we've protected our critical communications. Now, we have to protect the very foundation of the switched network itself, the spanning tree protocol, which is the thing that prevents catastrophic network loops.
On our access ports, the ports where users plug in, there are two features that work together as a team. First, you have port fast. That's for the user experience. It lets a computer get online instantly instead of having to wait 30 seconds for spanning tree to do its thing. Then you have BPDU guard. That's its security partner. It's like a safety net, constantly watching that port for any unexpected spanning tree messages, which would be a huge red flag that someone's trying to mess with your network.
So the main takeaway here is that these two features, port fast and BPDU guard, should always be used together on your end user ports. Port fast gives you the speed, and BPDU guard gives you the essential protection. And honestly, the easiest way to do it is just to use a single global command to enable both of them everywhere they should be. It ensures consistency and security.
And there we have it, our completed fortress. We started by locking down any unused ports. Then we put port security in place. We used static, hard-coded configurations to stop VLAN hopping. We built that critical foundation with DHCP snooping, which allowed us to enable DAI to stop ARP poisoning. And finally, we hardened the edge with port fast and BPDU guard. You can see how each piece builds on the last to create this really powerful, layered defense.
And all of this leaves us with one final thought to chew on. So much of what we just built comes down to this really simple idea of a port being either trusted or untrusted. But as our networks get more and more complex, more software-defined, is that simple binary distinction really going to be enough for the future? Or are we going to need more granular, more dynamic ways to assess trust? Definitely something to think about.